In section 3.2, we're going to start looking at polynomial functions and their graphs. We're going to look at some individual concepts, and then we'll put all those concepts together to graph at the end of the chapter. So the first thing we're going to look at is the end behavior of a polynomial function. And the text also will call this the leading coefficient test. And this is the behavior of the function as x goes to positive or negative infinity. Now, for any polynomial function, only the highest order or leading term, a sub n, x sub n, will determine the end behavior of the polynomial function. The other terms are irrelevant. Only the leading term will determine the end behavior. And it depends on two things. Is the leading coefficient a sub n positive or negative? And is the degree of the polynomial even or odd? The combination of whether the leading term is positive or negative and whether the degree of the polynomial is even or odd, that combination will determine the end behavior. Let's look at the case where n is even first. This might be the simpler case to understand. And you actually have already seen this behavior when we were graphing quadratic functions in section 3.1. The quadratic function is a polynomial. So let's look at f of x equals x squared. Notice, when the degree of the polynomial is even, the end behavior is always the same. That will be the characteristic of when the highest order term has an even degree. The end behavior will always be the same. When f of x is x squared, remember, we looked at the leading coefficient for quadratic functions. When it was positive, it would open upward. This is what your text would call rise left, rise right for polynomials. And remember, when the leading coefficient was negative for our quadratic function, it opened downward. This is what the text would call fall left, fall right. So think about our work with parabolas. That can really help you remember the even case for the leading coefficient test. Now, when n is odd, you will always get opposite behavior. And a good function, remember, is our cubic function. Notice here, the leading coefficient is positive. So this would fall left and rise right. When the leading coefficient becomes negative, it's really essentially a vertical reflection. And so now the behavior of the graph switches. This would be rise left, fall right. So remember, when your degree is even, the end behavior will always be the same. It will either be rising left, rising right, falling left, falling right. When the degree is odd, you'll always have opposite behavior. And so you really need to look at the sign of the leading coefficient. Let's look at example 1 on page 367 of your textbook. So f of x is x cubed plus 3x squared minus x minus 3. Again, only this leading term or highest order term matters to determine end behavior. The coefficient is actually 1, which is positive. The degree is 3, which is odd. So that combination, really very much like the x cubed function I just showed you, that would fall left and rise right. And generically, this is what the function would look like. You can look at figure 3.15 for a little more detail. But notice, it will fall left and rises right. Let's look at example 2 from your textbook. In this case, they've given us the polynomial in factored form, so it looks a bit different than example 1. This is a nice form we have to identify the zeros, which we'll get to shortly. But when we want to apply the leading coefficient test, again, we want to look at what's the sign of the leading coefficient and the degree of the polynomial. Now, one thing we don't want to do is multiply all these terms out and get the polynomial in the form that you saw in example 1. It's not necessary. First of all, we can see the minus 4 here. That's really going to be the leading coefficient. And so we know that is going to be negative. Now, how do we determine the degree of the polynomial? Well, there are actually 3 factors: x cubed, x minus 1 squared, and x plus 5. The degree of this factor is 3. If this term were squared, this x would become squared or have a degree of 2, and then this x has a degree of 1. So notice, I'll add the degrees of the individual factors. 3 plus 2 plus 1 is 6. That's an even number. And now the combination of a negative leading coefficient and an even degree, again, the behavior will be the same, but this will fall left and fall right. Now do pencil problems 3A and 3B. Now let's look at our next topic, zeros of polynomial functions. When we find the zeros of a polynomial function, or any function for that matter, we set that function f of x equal to 0. Just remember that real roots or solutions or zeros of f of x equals 0 will be the x-intercepts on the graph of that function. And that's really what we're looking for here as we move toward graphing polynomial functions. Let's look at example 5 on page 369 of your textbook. Now, we have this polynomial. We would set it equal to 0 to solve. And what we really are going to use, if you notice, there are 4 terms here with the polynomial. We'll use a technique called factoring by grouping. Now, anytime you try to factor a polynomial or even a quadratic equation, you always want to look for the greatest common factor. And that's how this technique gets started. So if we look at these terms here, the greatest common factor is x squared. So when I factor that, I get x squared times x plus 3. But now this factor can give me a clue as to how to factor this part of the expression. Minus times x plus 3 will give us this equivalent expression. And now notice the greatest common factor is x plus 3. So we can factor that factor out. And this would be times x squared minus 1, which equals 0. And now we can factor x squared minus 1. That is x plus 1 and x minus 1 equals 0. And then from here, from our individual factors, we will get x equals minus 3, minus 1, and 1. And so those would be our roots, or root solutions or zeros of this polynomial. And those would be 3 x-intercepts that would show up on its graph. We can then put those roots or solutions or zeros into coordinate point form, which we'll then eventually use to graph the function. Figure 3.19 on page 369 will show you the graph of this polynomial, and you'll clearly see these x-intercepts on its graph. Let's look at example 6 from page 370 of your textbook. So f of x is minus x to the 4th plus 4x cubed minus 4x squared. So we'll set that equal to 0. Now one thing we do, very often we like to have this leading term to be positive when we factor. So you can multiply this whole expression by minus 1, and that will change the signs of all the terms. So notice now it's positive x to the 4th minus 4x cubed plus 4x squared. Now, in factoring, again, you always want to start by trying to find the greatest common factor. The greatest common factor that will start with this polynomial is going to be x squared. So let's factor out the x squared. We'll get x squared times x squared minus 4x plus 4 equals 0. And now notice we have a nice quadratic function that we can still factor here. So f of x will be x squared times x minus 2 squared equals 0. Now that the polynomial is in factored form, we can identify its 2 roots, or solutions, or zeros. This is one factor. This root or solution will be 0. And then from this factor, that root will be 2. And again, we can put that into coordinate point form. So we would have 0, 0, and 2, 0. Let's look at the graphs of these polynomials from example 5 and example 6, because it will lead into our next topic, which is multiplicity of zeros. When we factored the polynomial from example 5, we had these 3 individual factors, which again we found those x-intercepts of minus 3, minus 1, and 1. And this is approximately what the graph looks like. Now, what you want to do is take a look at the factors and notice that technically each one of these factors has an exponent of 1. When we look at multiplicity of zeros, we'll look at that exponent. The textbook will call it k. And the idea is this. If k is an even number, an odd number, in which of course 1 is an odd number, then at these x-intercepts, the graph will cross the x-axis. So you see at each of one of these intercepts, the graph crosses the x-axis. Now, when we look at the graph from example 6, and this is the factored form, notice for each factor, right, the roots are 0 and 2, but now the factors have this exponent each of 2. And that value k, which we would refer to as the multiplicity, that is an even number. And if the multiplicity is an even number, then at the x-intercepts, the graph touches and churns at those intercepts of 0 and 2. So when you have odd multiplicity, the graph will cross the x-axis at the x-intercepts. When you have even multiplicity, it will touch and churn. So example 5 and example 6 are very good examples of this multiplicity concept that we're going to look at now. You can work on pencil problem 4 now to get practice on finding zeros of polynomial functions. Multiplicity of zeros is the next topic we'll look at. And I just previewed this topic looking at the graphs from example 5 and 6. So if we have a polynomial in factored form, generically we could call this x minus r to the k power, where r is really the root of that factor. There's really two cases. If k is an even number, the graph will touch and churn at that root, or r0 in coordinate point form. If k is odd, the graph will cross the x-axis at that point, x equals r or r0. And as k gets larger than 1, the graph will tend to flatten out at those zeros. Again, I had shown these examples. Notice here, the multiplicity is odd, or as a value of 1 for all these factors. The graph crosses the x-axis at all those intercepts. However, here, the multiplicity k is 2, it's even, the graph touches and churns at those intercepts. Now let's look at example 7 on page 371 of your textbook. So they give us this function, f of x equals 1/2 times x plus 1 times 2x minus 3 squared. And then they want us to identify the zeros and the multiplicity. Now when it's in factored form like this, it makes it a little bit easier. So we have two factors, x plus 1 and 2x minus 3 squared. The root for this factor is -1, and the multiplicity k is 1, which is an odd number. So what's the behavior? Well, the graph crosses the x-axis at the root or x-intercept of -1 and 0. For the second factor, the root will be 3/2, but now k is 2, which is an even multiplicity. In this case, the graph touches and churns at the x-intercept or root of 3/2 and 0. And the textbook will have a graph of this, but this is approximately what it looks like. Again, notice we cross the x-axis at -1, but touch and churn at 3/2. There's one last little topic I will include in this video that we're going to use when we graph polynomials, and that's the maximum number of possible turning points. And essentially, it's a very short formula. It's the degree of the polynomial -1. There's an example on page 373 of your textbook. This polynomial, x to the 5th minus 6x cubed plus 8x plus 1. The highest order term is x to the 5th. That means it's a 5th degree polynomial, so our degree n is 5. Its maximum number of possible turning points would be n minus 1, 5 minus 1, or 4. So you can look at that example in the textbook. Now do pencil problems 5 and 7.